Okay. So here we saw that 2.23 is the value for iron 2, right? And we said 2.12 is iron 3. That we got to know. Now, if you would think like iron 3 is high spin, that would be having only one parameter to contribute. Like for example, only lattice contribution is there, no valence contribution is there. Then do you think that delta EQ value would be this much similar if it is iron 3 high spin?
What, ma'am?
Say for example, here we are saying that in case of iron 3 high spin, we say that only one parameter is there. Only this is there, valence contribution is not there. Whereas in case of iron 3 low spin, it is having both lattice contribution as well as valence contribution. And in case of iron 2 high spin, it is having both of them there. And iron 2 low spin, that is D6, that would be having lattice contribution, but no valence contribution. Right? So what do you think? Like which of the two combinations are possible? If I am having one value for iron 2, iron 2 is having 2.23 and iron 3 is having 2.12. So these values are more or less like similar. They are not having much difference. So do you think like which possible combination is can be accepted over here? Is this A, B, C, D? So the combination could only be A plus D, B plus C, and B plus D. So which one is right according to you? Look at the values of delta EQ and then decide. Firstly, you need to see the delta EQ value is very high, which means that both the parameters have to be existing. Second thing, if they are very similar, what do you think that both of them would be including both the parameters or it is only one? So choose the right option among all the four things. And let me know.
B plus C, ma'am.
Okay, so B is iron 3 low spin and C is iron high spin. So you got to, you understood, right? Like how we are giving these values and how do we get to know about which combination is there when we are looking at the spectrum, right? So just looking at the spectrum, you can get to know about their oxidation state, whether they are high spin and low spin. So this is the case for the hemoglobin. Now we will quickly take up some examples from the iron complexes on which when assignment questions are being based. So generally we have mostly the iron complexes like in this particular form. So you might have heard about the Prussian blue and Turnbull's blue. So they both are said to having the same Mossbauer spectra, even though we have Prussian blue as Prussian blue's formula is iron 3, iron 6, 3. So here it is ferro So inside one, if you will see, this will become as iron CN6 4 negative, and outside is iron 3 positive. When you cross multiply it, that's why it becomes as iron 4 FeCN6 whole thrice. So this is the formula for Prussian blue, where the outside iron that is also coordinated with Cn with a different structure. It's in iron 3, and inner one is iron 2, which is bound with Cn. So this is the first case. Second, in Turnbull's blue, we have iron Fe CN whole 6. So this one is in 3 oxidation state, and the outer one is as a 2 oxidation state. We have here it is in +2 and here it is in -3. When you cross multiply it, so it becomes iron 3 Fe CN6 2. So outer one is in iron 2 and inner one is iron 3. Still we say that both the Prussian blue and Turnbull's blue, they give same Mossbar spectra. Why is it so? Firstly, we need to understand. Then in Prussian blue also, when we say that iron 4 Fe CN6 whole thrice, here outer one is iron 3, that is in high spin complex, and inner one that is iron 2, that's a low spin because it is directly coordinated with CN, right? So iron 3 high spin, it's D5. When we will put that, it will be having no valence contribution, lattice contribution. It is there because unsymmetrical binding with the CN. So the outer one, it is iron 4. So we don't know whether it looks like it is not symmetrical when it is come to the binding with CN. So we have 4 iron outside. They would be unsymmetrically bound with the CN. That's why lattice contribution exists in this case. And inner one, iron 2, low spin, that's a D6 low spin. And it is not going to have any valence contribution, as well as there won't be any lattice contribution because it is surrounded by only CN and CN. One iron is there and CN are there, which are symmetrically bound. Also, there is no Jandro distortion. So this iron 2 inner one is not going to have delta EQ. That means only one peak, and iron, this outer one, it is going to have splitting. So therefore, it is going to look like, the spectra is going to look like since I said this is, we already know when something is in iron 3, it would be going to have more delta negative value compared to the iron 2. So this is more delta negative. Firstly, we have to check, because until unless we know the values of it, we cannot directly comment on it. Firstly, we have to see that in case of iron 3 high spin, it was having delta EQ non-zero. That means splitting will occur. Whereas in case of iron 2 low spin, it is having delta EQ 0. So what do you think among, this is one peak and these are 2 peaks of one splitted peak. So if I'll draw it with different color, this one, what do you think, which one is for iron 3 high spin and which one is iron 2 low spin? Just on the basis of the delta.
Yes, ma'am. Fe plus 3 high spin. Fe plus 3 high spin, that is in red color, is a very big peak. Fe2 is in blue shaded colors.
I think you got confused. Just look at these values first. these one. We say that in iron 3 high spin, delta EQ is not 0. That means splitting will occur. Whereas iron 2, delta EQ is 0, no splitting. Now tell me,
Okay, ma'am.
which one is wrong?
Splitting is occur in Fe plus 3 high spin. So the blue shading color is a splitting of lines is available.
Right. So this is,
Splitting of peak is available. So that is for for Fe.
yeah, Fe3 high spin.
Fe
Earlier
plus
you
3
might
high,
have
high spin.
remember that normally when we assign the delta value, we say that our one oxidation state, if I'm saying that this is going to have more negative delta value, that is the case when we have kept the spin value constant. That means both of them either have to be high spin or they both of them have to be low spin. So the one parameter has to be kept constant, then only we can directly comment that this one is going to be the more negative or less negative. Say for example, earlier you said that earlier I also by mistake I wrote that this could be iron in 3 because it is having more negative value, but this is not possible when we are having both the parameters different. Both are in different oxidation state, both are making different spin complexes. So if both of them are different, the parameters are different. So there we cannot directly comment that whether which one is going to have more negative delta value or more positive delta value. Out of the two parameters, one has to be kept constant. If the oxidation state is constant, then we can comment on the spin complexes. If the spin complexes are spinning is constant, that both of them are making high spin or low spin, then we can comment on the +2 and +3 oxidation state. So is that clear? So in that particular aspect, look at the splitting. Splitting will give you more better idea, like which among both of them, which one is going to be splitting and which one is not going to be splitting. If iron 3 is going to split, so it is very clear that the right side is the splitting of one peak and the left side it's not the splitting at all. Therefore, the left one is the iron in 2 low spin. So is this clear? Hello.